So at this stage, I'm willing to know, if I know the Laplace transformation of a function, can I predict the Laplace transform of that function's derivative? And if we can know that, then a lot of the relations, and a lot of the Laplace transformations to be specific, can be found out just simply by differentiating things. So for example, if I know about the Laplace transform of, for example, let's say t squared, then I can easily find out the Laplace transform of t, and then Laplace transform of 1. You see the connection? Because Laplace transform is linear, I can make all those transitions. And that is why it is particularly important for us to know about the Laplace transformation of derivatives. We'll start with the first derivative, and then progressively go for higher derivatives, and then possibly we'll try to find out a general result. So let's start. The Laplace transformation of the derivative can be found out directly from the definition. So we plug into the integration from 0 to infinity e to the power negative st, and then f prime of t dt. What we can do is to change our integration variable from dt to df. So as before, we'll write the limit from 0 to p, where p goes to infinity at the end. And then of course I can write e to the power negative st and then df. Okay? So this is not quite correct because I have changed the integration variable but still kept the limits same, right? So mathematically it's not a valid thing to do. But for now we are going to ignore that, and we would like to continue with this because we recognize that this form in this integral is particularly similar to a form we are already familiar with, and that is the integration of u dv. And that is given by, well, in the form of antidifferentiation, uv minus v du, and there is an integration over the last term. So what do we get? We get, well, first of all, e to the power negative st and then f of t, okay, and of course the limit sits from 0 to p. Well, 0 means t equal to 0, so let me write that. And then I have v du. Well, u is e to the power negative st. So what happens is there is a negative sign, right, like here, but there's also a negative sign from negative s. So two negative signs make it positive, and then we have s integration from 0 to p e to the power negative st f of t dt. But this is good for us, right? Why this is good for us? Because this integral is something that is familiar to us, and that is the integral we have here in the original question. So this is simply f of s. Okay? So now what we do is just simply substitute the values, the limiting values, in the first term, and notice what we get. So once again, the limit persists, p tends to infinity, and then for the first term I get e to the power negative sp, so e to the power negative sp, and then f of p. And for the second term we get minus, well, e to the power 0, which is 1, and then f of 0. Well, this one is devoid of p, and therefore if we take the limit on this term, this doesn't change. Okay, what about the next term? We have plus s from 0 to p, e to the power negative st, and then f of t dt. Okay? So, now the next step is really simple. If we take p tends to infinity, this term here goes to 0. So left with two terms only. Well, this one turns to s times f of s. So we have s times f of s, which is the second term here, underlined one. And then, of course, this term right here. So for this one, we get minus f of 0. And that is the integration, the Laplace transformation of the derivative of f with respect to t. Now, in order to find out this formula, we have actually overlooked a lot of subtleties and nuances and conditions that comes up with every theorem, right? Every theorem has its own conditions under which the theorem is true, and those conditions will give you a hint when that theorem might be violated. And this formula actually can be casted as a theorem. And so therefore, it should have its own baggage of conditions. So here we have to have, for example, f of t to be continuous, right? So continuous within an interval. So for example, 0 to some number n, and then it needs to be of exponential order, right? So we have discussed about exponential order. It has to be an exponential order after that interval, okay? And then f prime of t will have to be, for example, sectionally continuous. So sectionally continuous within this interval 0 to t, 0 to n, for example. So these are the conditions for this theorem to hold true. But don't worry, if these things any of these things doesn't hold, then we have to modify this theorem in some way, and they will come up in appropriate places. So unless they don't come up, I don't want to give you sort of a list like when it might go wrong. So if that situation comes up, I'll first introduce that concept, and then I'll move on to show you examples. Now, the second step is to find out the Laplace transformation of, for example, the second derivative of this function. What happens? Well, we know about the first derivative, right? So all we'll need to do is to first substitute this into the formula we have just derived, and that will allow us to generalize it to the second order and then third order and then for arbitrary order of derivative. And what I believe is that if I just show you the second order, you'll understand the vibe, and I can then write down the general formula. So for the second order derivative, all we'll need to do is to first write s, and then we have the Laplace transformation of the original function. Well, in this case, the original function is the first order derivative, and so we'll have to write the Laplace transform of the first order derivative, right? And then minus the first order derivative evaluated at 0. Well, we know the formula for this one, and then we substitute, so we get the Laplace transformation of the first order derivative is given by s, and then we have f of s, and then minus f of 0, right? And then minus f prime of 0. So that's it. That gives us essentially the result. So the Laplace transformation of this second order derivative is equal to s squared and then f of s, which is the Laplace transform, minus s times f evaluated at 0 minus the derivative of f evaluated at 0. This is a very useful result, and I suggest you should memorize it, at least for future purpose. Can I generalize this formula easily? I believe I can. So for example, the Laplace transformation of the nth order derivative, where n is arbitrary, right? So I write n of t. So this means nth order derivative of the function capital F with respect to this variable t. and that gives us s to the power n f of s, and then minus s to the power n minus 1 times f evaluated at 0 minus s to the power n minus 2, and then f prime evaluated at 0, and this go on, and then in the last part we get s and times f of n minus 2, so it's the derivative n minus 2 evaluated at 0 minus f differentiated in minus 1th time evaluated at 0. And of course the conditions related to the existence of this formula is subjected on the fact that all these derivatives, they are continuous, and continuous in some domain which is 0 to t to n. So here they are continuous, and after n they are of some exponential order, and of course f n of t has to be sectionally continuous. So in the next video I'm going to show you some examples related to this formula.